Section 6.2, Volumes and Average Values. In this section, we look at two more applications of integration. The first is finding volumes of solids with a known cross-sectional area, and the second is computing the average value of a function on an interval. For the first, let's consider a solid, which when we slice it in either the x direction or the y direction, we are able to compute the area of a cross-section. So here's just a prototypical example. Suppose that we have this blue solid and we want to slice it. In this example, we will slice it such that the thicknesses are thicknesses in the y direction. And so when we look at these slices, if we just pick a representative slice here, which we'll just pull this one out, notice that representative slice sits at some height y. And if we look at that slice, it has a thickness in the y direction that we'll call delta y or delta yi, since the each slice could have a different thickness. So they could change as the slices change, but they have a thickness in the y direction. And if we think of this as infinitesimally thin, think of a really, really thin, something like a penny or even smaller than that, then to find the volume of this slice, since its thickness is infinitesimally thin, just think delta y, then we really just need to know the area of the face. And so if that area of the face is something that we can figure out the area of, then we'll be able to figure out the area of the slice by just taking the area of the face and multiplying by the thickness, and assuming we know how to do this. Different geometries, this will be a different calculation, but suppose that we can find the area of the face, then the area of the face could easily be a function of the slice height, and we multiply by the thickness. And then if we wanted to find the total volume, we would just sum the areas. We would sum the volumes of all the slices. So we'd sum the areas times the thicknesses. So this is just summing the volumes of all the slices. And then we would take the limit as the number of slices goes to infinity. When we do that, this Riemann sum becomes an integral. We'd integral from some low y value to some high y value, so from say a to b, and then the integrand would be a of y, which is our cross-sectional area, and our differential is dy. So in essence, this shows us that the volume is the integral of the cross-sectional areas. So if we ever have a shape such that when we slice it, we're able to find the cross-sectional areas for the varying slices, then we'll be able to compute the volume via an integral. Let's look at a concrete example of this concept. Let's find the volume of a cone which has a radius of 1 and a height of 5 using integration. Now I know we could find the volume of the cone using a basic middle school geometry formula, and that's not really the purpose. The purpose is to see how to do this using calculus. And truthfully speaking, the way that you got that formula in middle school geometry, they never really explained where that formula comes from because it comes from calculus. So we'll see that this process here, if we have a cone, we'll say that it has a height of 5, it has a base radius of 1, and so what we want to think about doing here is slicing this in a geometrically friendly way. So we could slice this where our thicknesses are in the x direction, so we make these vertical slices. But if we made these vertical slices, if you can envision that, they don't have a very friendly geometry. It's not easy for me to tell you what the volume of an individual slice is. On the other hand, if we slice it where the thicknesses are in the y direction, so we have these horizontal slices, then because the cone has the circular symmetry in this direction, we would get these thin little discs or thin little pennies, these thin little cylinders, and we have a chance at finding the volume of that little slice. Okay, so let's label some things. So notice this is how you're going to start every one of your problems. You want to get a very clear picture of what's going on. You want to label the relevant quantities. Then you want to pick what direction are you going to slice it in. Here it really only makes sense to slice it so that the thicknesses are in the y direction. And when we do that, I'm just going to draw one representative slice. Really, we'd have lots and lots and lots of slices, sort of like we had up here. But I don't want my picture to get too busy, so I'll draw one representative slice. And that representative slice, notice it could have been down here, it could have been here, it could have been here. So it has some slice height. That slice is sitting at a certain height that we'll call y. And once we're looking at this slice, it has a thickness in the y direction, so its thickness is delta y. It looks like a thin little cylinder with a thickness of delta y, And then the radius of this little cylinder or this little disc is this distance x. And so the radius is a distance in the x direction. We could call it r, but I'm labeling it as x because it's a distance in the x direction. Now we need to coordinatize things here because we need to figure out what the volume of this little slice is. And we could say, well, the volume of the slice is the area of the face times the thickness. So here's the area of the face. The face, you can see, is just a circle. So its area is going to be pi times the radius squared. The radius here is x. We don't know what x is yet. And x changes. Notice that when your slices are up here, x is very small. When your slices are here, x is medium. And when your slices are here, x is the largest that they're going to be. So we have the area of the face, which is pi times the radius squared times the thickness, and the thickness is delta y. And so this is where we want to be very careful and sort of read our keys. We don't have any control over this thickness. It's delta y. And since that's a delta y, we know we're eventually going to integrate with respect to the y variable. Our hand is forced. We're going to integrate with respect to y, and if that's the case, then the thing we're integrating better be a function of y. So right now, the thing that we're going to be integrating is a function of x, so we need to write x as a function of y. And we see when we look at this picture, as y changes, the x's are going to change. So there's a dance taking place between the x and the y variables, and we need the relationship between the x and the y variables. This usually comes from the geometry of the situation. So if we coordinatize things to try to get a feel for what the xy relationship is here, if we just take a slice right down the middle of this cone so that we get a two-dimensional figure instead of a three-dimensional figure, we see here the edges of the cone, here's the base of the cone, here's in blue is our representative slice. Its thickness is really, really thin, but it's a delta y. This is the slice height, and this was the radius of that little disc here, trying to keep the color coding scheme the same. So let's be very careful in how we label things. This is 1, this is 5, the height of the overall cone. And then if this is y and the overall height is 5, then this distance here must be 5 minus y. So we'll write that over here. So let's keep our eye on the prize. We're trying to find a formula that relates x to y because we need x as a function of y here so that when we form an integral, we know we're going to have a differential in y, so we need to have an integrand that has y's in it, not x's. So we look over here. Now, truthfully, there's several different ways that you could do this. I'm just showing you one of them. But one way to do this is you could use similar triangles. You could notice that this little triangle, this little right triangle, is similar to this big right triangle. And so that means their sides are in proportion to one another. So for example, you could say the vertical side of the small rectangle, of the small triangle, is this length is to this length is to this length, as this length is to this length. So for example, the vertical length of the short triangle is to the vertical length of the big triangle, as the horizontal length of the small triangle is to the horizontal length of the big triangle. So that would give us the ratio 5 minus y is to 5 as x is to 1. And that's exactly what we need. We have a formula that relates x and y. Now we just need to finish things off, and we need to isolate the x. We want to solve for x as a function of y. So if we do that, we just cross multiply, then we divide through by 5, and this is what we wanted. We now know how x changes as well. You know what the value of x is for any given y. You could have also done this another way. For example, what we're really just doing is finding the equation of this red line, because this red line is tracking this xy pair. Notice that is x comma y right there. And you could find the equation of this line. You have 2 points that live on the line. You know that 1 comma 0 is a point on the line, and you know 0 comma 5 is a point on the line. So you could just calculate the equation of the line through those 2 points. And normally you would do that as for y as a function of x, but if you solved for x instead of y, then this is exactly what you would get. You can try it and see. The bottom line is we now know x as a function of y, and when we do that, we can substitute what we have, x as a function of y. Don't forget, it's still squared because of the square here, and we now know the volume of the slice. So if you zoom out for a moment, you notice that even though we've done lots of good math, we've done no calculus this whole way. And this will be a common thing in your work. You'll spend most of your time, energy, and effort getting a good picture, understanding how to play the game, understanding how to find the volume of a slice, figuring out what exactly you need to solve for. Do I need x in terms of y or y in terms of x? Figuring out the proper geometric relationship that will allow you to unlock those things. And then we're about ready to do calculus, because once we have the volume of a slice, then we can say that the total volume is just the accumulation or the integration of all those volumes of the slices. So notice we're just integrating what was the volume of our slice, and now we approach this integral and we say, okay, how do we do this integral? You could do this integral with just using algebra or using a u substitution. Here I'll use algebra just to give us a little bit of a different change of pace, but you could do this with a u substitution. And so when I do algebra here, I'm just going to square this out. So remember, when I have this a minus b quantity squared, that's just a squared minus 2 times a times b plus b squared. So I'll pull the pi out here. Still have an integral from 0 to 5. I'll square the first term. I'll double the product of these two terms, and then I'll square this last term. Remember, you're squaring this entire last term. Okay, so now this is an integral that's doable by linearity and the power rule. So if we just antidifferentiate the pieces, then we evaluate the antiderivative at 5 minus the antiderivative evaluated at 0. And when the algebra dust settles, we get that the volume of the cone was 5 pi over 3. And of course, you could use the elementary volume formula, 1/3 pi r squared h, and you would see that you get a 5 pi over 3. So the point wasn't really just to get the volume of the cone, it was really to understand how this process of slicing, working on the volume of a slice, working on the micro level, and then accumulating to answer the macro question. Okay, let's look at another example. Let R be the region bounded by the square root of x and y squared, y equals x squared. R forms the base of a solid whose cross sections perpendicular to the y-axis are squares. Let's find the volume of this solid. So this is an example that's recycled, or a region that's recycled from our last section, where we had the top curve was y equals the square root of x, the bottom curve is y equals x squared. We're looking at this green region is going to be the area between those curves, and we are going to let this be the base of a solid. And then there is a solid coming out of the screen at us, and the description says that R forms the base of a solid whose cross sections perpendicular to the y-axis. So we're going to slice in this direction, perpendicular to the y-axis. They're going to be squares. So for example, here I'm just going to look at a representative slice, and then coming out of the screen at me, so if this has length L, and we'll figure out L in just a moment, but if this has length L, and this length sits at a slice height of Y, but if this length L is sitting here, then this is L, and coming out of the screen at me is a square, I can tell that the thickness, because I sliced it this way, the thickness is in the Y direction. It's a very, very thin slice where the thickness is in the Y direction, and so the thickness is delta Y, but because they told us that it's squares, this length and this length must be the same. So if I can find just this length L, I'll be able to do the volume of the slice, because the volume of the slice is just the area of the face times the thickness. Well, the thickness is delta Y. The face is just a square, so it's L by L, so it's L squared. And now I read my keys and I see, since the thickness is delta Y, I must know L as a function of Y. I need to be integrating with respect to y, so I need L as a function of y. Okay? But if you look at this, similar to the last section, this length L is just the distance that we get when we look at the right curve minus the left curve as functions of y, not functions of x. So why don't we translate these curves and rewrite y equals the square root of x. If we square both sides, we get that the description is x equals y squared. And similarly here, if we take the square root of both sides, x is the square root of y. So the L, which is the right curve minus the left curve, the right curve is square root of y, and the left curve is y squared. So I get square root of y minus y squared. So that means the volume of my slice, which we said above, was L squared times delta y. L is now this quantity, So I get the square root of y minus y squared, still squared because the L was squared, delta y. And here comes the calculus. Since we got the volume of the slice, we know that we can get the total volume just by integrating or accumulating the volumes of the slices. So this was the volume of my slice. And we do need to concern ourselves with the limits of integration. But we look at this dynamic process. Remember, we're slicing. And when we slice, our slices, our slice height y, our slices could be as low as y equals 0. And then they work their way up. And a slice could be as high as y equals 1. Not x equals 1, but y equals 1. So we're going to be integrating from y equals 0 to y equals 1 because this is how our slices are going. So this gives us the integral from 0 to 1 of the square root of y minus y squared, quantity squared, dy. This is not doable by a u substitution. We need to use algebra. And so here we're just going to multiply this out. And so we'll get the square of the first term minus 2 times the product of these terms plus the square of this term. Okay. Notice this is a y to the 1/2. So when we multiply it by a y squared, we get y to the 2 plus 1/2, which is y to the 5/2. And now we just anti-differentiate this with the power rule and linearity. We get y squared over 2 minus, leave the 2 alone, y to the 7/2 over 7/2 plus y to the 5th over 5. We evaluate that from 0 to 1. And when the arithmetic dust settles, we get a 9 over 70 as the volume of the solid. Okay, so we gave you an example where you're integrating in the x direction and another example where you're integrating in the y direction. And hopefully that will give you some examples to go by. Honestly, the best way that you learn this is after seeing a few examples, whether you've seen 2 examples or 22 examples, is you just have to jump in, try some things, get some things right, get some things wrong, and just keep referring back to the process that was in these examples on how to do these. Okay, the last topic that's in this section is a quick one, and it's finding the average value of a function on the interval from a to b. Remember, chapter 6 is all about applications of integration. So in the previous section, we saw that you can find the area between curves. Earlier in this section, we saw that you could find volumes of solids with a known cross-sectional area. And here yet again is another application of integration. You can find the average value of a function on an interval. And we're going to define that as 1 over the length of the interval times the area under the curve. So if you think about it, what we're doing is we're defining the area, we're defining the average value to be take all the area that's under the curve, f, from a to b, and divide it over the interval length, or evenly distribute it over the interval length. Notice this is a number, and this number is what we tag as the average value of the function. Okay, so as a concrete example, let's find the average value of the square root of x on the interval from 0 to 4. So from the average value formula, I'm going to do 1 over b minus a, integral from a to b of f of x dx. So this is going to, if I rewrite this as a 1/2 power, and then I anti-differentiate, and I evaluate between limits, I get that the average value is 4/3. Okay, but what does that mean? Geometrically, we'll show you a picture here in just a second. This means that a rectangle whose base is 4 and a height of 4/3 will have the same area as the area under f of x equals the square root of x on 0 to 4. I think a picture is worth 1,000 words. So what in the world does this 4/3 mean? It means that if you take a look at the graph of y equals the square root of x on the interval from 0 to 4, and you look at that function, and you look at the area that's under that curve, that what we want to do is we want to take all this area under the curve, we want to divide it by 4, and see what number we get. And when we do that, we're going to get the number 4/3. That's what the calculation did. What that says is if we were to look at a rectangle whose base is on the interval from 0 to 4 and whose height is 4/3, that this green rectangle would contain exactly the same amount of area as the area, the red area, the area under the curve. So that's what the average value is doing. It's balancing the area under the curve by evenly distributing it across the interval. This is a very useful concept in a lot of physics, all sorts of applications, finding the average value of a function. For example, let's find the average value of the areas of all circles whose radii vary from r equals 1 to r equals 6 inches. So here our function would be the area function for the circle, so it would be pi r squared. And our interval is going to be an R interval where R ranges from 1 to 6. So we would have 1 over b minus a, integral from a to b of our function. Our function is a function of r, so we're integrating with respect to r. So this would just give us a 1/5. We'll pull the pi out. We'll antidifferentiate the r squared to get r cubed over 3. We'll evaluate that from 1 to 6. When we do that, we clean things up just a little bit. We get a pi over 15 times 6 cubed minus 1 cubed, which when you simplify that, you get 43 pi over 3. Okay, so now you ought to be able to do, the homework is going to consist of problems where you're finding volumes with known cross-sectional areas, and it will also have some average values, so you have a chance to try both of these things.